Picture a modern vehicle pulling into your service bay. There's no engine roar, there's not a single vibration, no exhaust fumes filling the air. Beneath the floorboards of that quiet cabin sits a high-voltage electrical system, pushing upwards of 400 volts. If a technician treats every vehicle with an electric motor as the exact same platform, the immediate result is hours of wasted diagnostic labor. The worst outcome is a lethal safety hazard. You have to start with what we call the triage protocol. This is a strict visual and systemic sorting of the vehicle into one of three distinct categories: HEV, PHEV, or BEV. Guessing the system architecture without verifying it first is a critical diagnostic failure. Knowing exactly what type of battery system you're dealing with dictates your safety procedures, the data you pull from your scanner, and exactly how you troubleshoot the problem. Triage begins with a physical inspection. We find a combustion engine under the hood, but the exterior lacks any sign of a charging port. This specific configuration defines the hybrid electric vehicle, or HEV, which operates with a small battery pack typically limited to 1 or 2 kilowatt-hours. Because there is no external plug, all energy comes from an internal loop. The battery is charged entirely through regenerative braking and by siphoning mechanical power from the combustion engine itself. Customers will often bring in an HEV complaining that they can't find the charging port. Your answer as a technician is simple. It doesn't have one. It manages its own charge. The next branch on the triage tree is a 50-50 split system. If you see a combustion engine, an 8 to 20 kilowatt-hour battery, and a dedicated plug on the exterior, you have a plug-in hybrid electric vehicle, or PHEV. That larger battery allows the PHEV to drive entirely on electric power for moderate distances. Once that battery hits zero, the internal combustion engine automatically fires up to take over the drive cycle. This creates a unique diagnostic scenario. A customer might bring in a PHEV that drives perfectly fine on gasoline, but refuses to accept a charge from a wall outlet. That points you immediately toward the onboard charger, the physical socket, or a failure in the charging communication network. For both HEVs and PHEVs, the combustion engine acts as a mechanical safety net. Even if the high-voltage electrical system completely fails, the vehicle can usually still physically move. The final branch of the triage tree requires striking out any sign of combustion hardware. No engine, no exhaust pipe, just an external charge port and a massive battery pack ranging from 40 to over 100 kilowatt-hours. This is the battery electric vehicle, or BEV. It is a pure, single-source electrical architecture, with the high-voltage battery filling the entire floor pan and driving the motors directly. You will encounter this architecture in vehicles like the Tesla Model 3 or other modern vehicles like the BYD Atto 3. Because there is no combustion engine to fall back on, the diagnostic reality is absolute. If the main battery drains completely or a high-voltage component faults out, the vehicle goes completely dead. There is no plan B. When a fully dead BEV arrives, you follow a strict three-step protocol. First, visually confirm the BEV classification. Second, locate the manual service disconnect, or MSD, so you know exactly how to physically sever the high voltage if needed. Third, connect an EV-specific scan tool. On that scanner, you are pulling specific metrics like the state of charge percentage and searching the log for high-voltage isolation fault codes. Without a mechanical backup engine to get the car moving, your ability to strictly read and interpret that electrical data is the only way to resolve the failure. BEVs eliminate the need for oil changes or spark plug replacements. Instead, the workload shifts toward interpreting complex digital algorithms and diagnosing high-voltage battery chemistry. This chart shows how critical that chemistry is. The top line represents the battery's state of health, or SOH. As the SOH percentage drops over time, the lines representing the vehicle's maximum driving range and its monetary resale value plummet right alongside it. For a century, the automotive workshop relied entirely on physical labor, turning wrenches on heavy iron engine blocks to keep cars on the road. Today, resolving an issue means navigating high-voltage data networks and safely verifying voltage drops across complex battery arrays. Mastering the triage protocol and high-voltage diagnostics provides the essential skill set required for the silent, electrical future of the automotive industry.